All right. Chapter 6. Chapter 6, we're going to focus on normal probability distributions as opposed to the binomial probability distributions that we covered in Chapter 5. Now, the binomial distribution was an example of a discrete probability distribution. If you recall, a discrete distribution is one where the variables take on a finitely many values. But in a continuous distribution, you have variables that take on infinite number of values. The normal distribution is the most important example of a continuous probability distribution. The graph of a normal distribution is also called a normal curve. And it kind of possesses a shape very much like that of a cross-section of dry sand. Because of this, blacksmiths would sometimes use a pile of dry sand in the construction of a mold for a bell. So the graph of a normal distribution is called a normal curve. It's also called a bell-shaped curve. If you ever heard the term bell curve before, teachers use bell curves all the time when it comes to curving grades. So here's an example of a normal curve. Now, what are some things that we notice about this curve? Well, the highest point is here. And notice where it's pointed at. It's pointed at the average. And what happens here is you have what's called inflection points where the behavior of the graph, and this is mentioned in calculus too sometimes, that the behavior of the graph changes from increasing to decreasing and so on and so forth, right? Or the shape of the curve changes. And those happen within one standard deviation of each other. And then going towards the left, the curve decreases. Going towards the right, the curve also decreases here. Now, the mean and the standard deviation of a normal curve is super important here. So the standard deviation actually controls the spread of the curve. So what we're going to see here is, in this example, the curve, in both instances, the curve is close to the horizontal axis at the 3 standard deviation mark. Okay. And so remember when we talked about standard deviation in chapter 3, one of the things we mentioned was that the larger the standard deviation, the more spread out your standard deviation is. The smaller your standard deviation is, the less spread out, the more condensed your data is. Here's an example of a standard deviation that's large. The data is more spread out in the bell, but if your standard deviation is smaller, it's more condensed in the data. Because again, standard deviation represents how far the data is spread from the center. Talked about inflection points a little bit earlier. So going back to the example curve from earlier. So here is a normal curve cupped downward for an interval on either side of the mean. And it begins to cup upward as we go towards the lower part of the bell. So the transition places where these occur, these are called inflection points. And those inflection points happen within one standard deviation from the mean. So it's the mean plus standard deviation and the mean minus the standard deviation. And like I said, in terminology of calculus, these are called inflection points. Now, here's some important properties of a normal curve that you should know. So the curve is always going to be bell-shaped with the highest point over the average. Now, why is that? This is one of those cases where the average, the median, and the mode are the same, right? So the mean represents the average of the data. It also represents the median, which is why it's right in the smack dab in the middle of the curve. And it's also the number that appears most often, which is why the curve is so high at the mean. And it's also symmetrical through the mean. It's also symmetrical about the mean. It's and that's always, a bell curve will always be symmetrical. And it will always approach the axis, but never touches it or crosses it. A normal curve will never cross the x-axis of or the horizontal axis of your graph. And then, of course, we talked about those inflection points happening within one standard deviation from the average. And of course, because we are talking about a probability, the entire area under the curve is equal to 1 because that represents all of the probabilities of your distribution. Now, what actually controls the shape of a normal curve? Two things control it, the mean and the standard deviation. When you have a specific mean and standard deviation, you can create a specific normal curve. In general, the average, the mean, locates the balance point, and the standard deviation determines the extent of the spread. So let's practice identifying mean and standard deviation. So look at curves A and B. Do these distributions have the same mean? Well, they do. Where are they symmetric at? They are symmetric at this point. So for both of these, the average is 6. One of the curves corresponds to a normal distribution with a standard deviation of 3, and the other one with a standard deviation of 1. Which curve has which standard deviation? Well, again, the larger standard deviation, the more spread out your data is. The smaller your standard deviation is, the less spread out it will be. Looking at these two curves, the larger standard deviation corresponds with the more spread out data. In this case, it would be B because it's more spread out. It's more elongated. Whereas with 1, that's curve A. The data is more condensed here. So what does a normal distribution tell us about probability? Well, as I mentioned before, the total area under any normal curve will always be 1 because it's the accumulation of all of the probabilities of your distribution. The graph of the normal distribution is important because the portion of the area under the curve above a given interval represents the probability that a measure will lie in that interval. Let me say that again. The area under the curve above a specific interval tells you the probability that a measurement will lie in that interval. And that leads us to what's called the empirical rule. We mentioned Chebyshev's theorem early on in, I believe, chapter 2. The empirical rule is a more specific version of Chebyshev's rule. So with normal distributions, the smallest proportion of data will lie within 2 to 3 or however many standard deviations of the mean you go up towards. In order to know what proportion of data lies on each side of the mean, we use what's called the empirical rule, and here it is. For a distribution that is symmetrical and bell-shaped, and specifically for a normal distribution, 68% of the data will lie within 1 standard deviation on either side of the mean. That's this area right here in the center of the curve. Approximately 95% of the data values will lie within 2 standard deviations on either side of the mean. So here's 68% from here to here. That's 95% of the data. And then approximately 99.7%, or almost all of the data values, will lie within 3 standard deviations on each side of the mean. So the stuff that we can see all right here, that's 99.7% of the data. Now, the other 0.3% might account for outliers and such. So be aware of that. But almost 99%, 99.7% is within 3 standard deviations of the mean. Now, what does that mean for each individual section? So what percent values go under the curve in each section? Well, first off, we know that this graph is completely symmetrical. So from here to here is 68%, which means that each individual section on either side of the mean is 34% of the data. Now, when we go out further to that 95% of the data, well, I already have 68 here, which means that the remaining 2 pieces, that's about 27%. Well, that's for both of these, so I got to divide that in half for each section. So that's about 13.5% for these little guys right here. Then we go out to these puppies here. So all of this is 99.7%. Well, we already calculated 95% of that. So that leaves us with 4.3%. 4.3% left. I'm sorry, not 4.3, 3.3% to deal with here. So if I take that 3.3 and divide that by 2, no, I'm sorry, I did have it right the first time. Apologies, I'll start over. So this is 99.7%, this is 95% here. So these puppies account for 4.7%. Now if I divide that by 2, that means each of these puppies is 2.35%. 2.35%. Well, what about the rest? Well, 99.7% is pretty much everything under the curve from within 3 standard deviations of each other. So that means that both this area and this area account for 0.3% of the rest of the data, which means each side accounts for 0.15%. And that's how much of the data goes into each section of that curve using the empirical rule. Let's look at an example. The yearly wheat yield per acre on a particular farm is normally distributed with a mean of 35 bushels and a standard deviation of 8 bushels. Shade the area under the curve that represents the probability that an acre will yield between 19 and 35 bushels. Well, again, now why these values? Well, the standard deviation is 8, right? So if I subtract 8 on both, if I add and subtract 8 on both sides of 35, 35 minus 8 is 27. 35 plus 8 is 43. Each of these represents 1 standard deviation, which means that these represent 2 standard deviations for the mean. If I continue to subtract 8 on this side, I continue to add 8 on this side. Okay. Well, where's the area of the curve that represents the probability that an acre will yield between 19 and 35 bushels? Well, here's that data. Here's that shaded area right here. Is the area the same as the area between the mu minus 2 standard deviations and the mean? Well, the mean is 35. And if I take 35 times 2 times the standard deviation, which is 8, that's 35 minus 16, which is 19. And yes, it is the same area between this and this, right? So the question is, what percentage of the data over that interval is between 19 and 35? Well, here's the mean, which means that everything on the left side of it is half the data. I know that this side right here is 34% of the data. Okay. And then also we calculated that, see, 95 minus 68, that was 27. 13.5. So 27 for both of these sections, which means 13.4 for each little one. Well, if I add those together, 34 and 13.5, I get a total of 47.5%. Another way to look at it is this. From here to here, this is 2 standard deviations. So from here to here, actually I can make that a little bit better. From here to here is 95% of the data, which means that 5% is spread out between here and here. And dividing that evenly by 2, that's 2.5%. So if I subtract that from 50%, that's where I get that 47.5%. So that means that there's a 45% chance that a data value will fall here in this interval here. What is the probability that the yield will be between 19 and 35 bushels per acre? Right there, 47.5%. So all in all, what does a normal distribution tell us? Well, it tells us, again, the area under the entire distribution is 1. The area over a specific interval of values from A to B is the probability that a randomly selected value falls between A and B. The distribution is symmetrical and mound-shaped and is centered over the mean. And most of the data ranges from within 3 standard deviations. Now, where does this occur actually? Well, a lot of things use a normal distribution. Heights of people, size of things produced by machines, errors in measurements, blood pressure, even grading. Like I said, teachers use bell curves a lot when it comes to grading. Here's an example. 95% of the students at school are in between 1.1 meters and 1.7 meters tall. Assuming this data is normally distributed, what is the mean and the standard deviation? Well, first off, I can find the mean easily by finding the median between these two values. Because remember, it's symmetrical. So whatever the middle of this value is, of these values are, that's your mean. So if I find the midpoint here of these values, 1.1 plus 1.7 divided by 2, that's 2.8 over 2, which is 1.4. Now, to find the standard deviation, again, let's go back to the empirical rule. 95% of the data lies between 1.1 and 1.7 meters tall. That means that the average, plus 2 times the standard deviation is equal to 1.7. And the average minus 2 times the standard deviation is equal to 1.1. Well, it's a good thing I know what my mean is. It's 1.4. So let's substitute that and solve for the standard deviation. 1.4. All right, here I'll subtract 1.4 on both sides. This is 0.3. Divide both sides by 2. Standard deviation is 0.15. Let's see if it's the same here. Subtract 1.4 on both sides. -2 standard devs equals -0.3. Divide by -2. Negative times negative is a positive. I end up with the same value. So 0.15 is my standard deviation here. Okay. Using the mean and standard deviation, draw out this normal distribution. Okay. Well, again, my mean is 1.4. Standard deviation is 0.15. So I'm going to go ahead and draw out my horizontal axis. I'm going to put the mean right square in the middle. So that's 1.4. Here's 1 standard dev, 2 standard devs, 3 standard devs. 1 standard dev, 2 standard dev, 3 standard dev. Now 1.1 and 1.7, excuse me, were the 2 standard dev mark. What about the 1 standard dev mark? What about my inflection points? Well, if I take 1.4 and I subtract 0.15, I get 1.25. And if I add on the other side of that, 1.55. And I'm going to add the standard deviation again here to 1.7. And then I'm going to take 1.1 minus 0.15 to get my 3rd standard dev mark on the other side. Here is my mean. I'm going to try to make these curves as accurate as possible so that they line up. well enough. Just want to make sure that they line up the way they're supposed to, so that they don't go below the horizontal axis. Now, here's another example. A survey of daily travel time had these results in minutes. Here is your data. Find the mean and standard deviation of this data set. So here's a trick. I'm going to show you guys a really cool trick to do with your calculator so that you don't have to waste time here. So remember when we did, when we try to list data here with the stat button. So with the stat button, if I go to edit, here in L1, I've already typed in the data here, okay? So you just type in all of your data set here, and when you're ready, you press the stat button again, scroll to the right one time, where it says one variable stats, number 1, that's what you're gonna choose. And so my list here is L1, I'm gonna keep that as my list. I'm gonna calculate, and it gives me the mean and the standard deviation. The mean here, all the way at the top, 38.8. My standard dev, 11.4. So that's what I'm going to use on this, okay? So mean is 38.8, standard dev is 11.4. Again, put my average in the middle. 1, 2, 3. 1, 2, 2, 3. Here's 38.8. Going to subtract 11.4 to get this side. Minus 11.4, that's 50.2. Oh, sorry, I added. You know what? I'll just add first before I subtract. 50.2, 61.6, and 73 on the other side. $27.4, 16, 4.6. Again, I'm going to draw out my points here on the curve, making sure that my data is nice and evenly distributed. So again, this represents 1 standard def from the mean, 2 standard defs from the mean, 3 standard defs from the mean, and same thing on the other side. 1 standard def from the mean, 2 standard defs from the mean, 3 standard defs from the mean. There is your normal distribution chart. Now, a big part of normal distributions is used in control charts. So when we examine data over a period of time that's equally spaced in time intervals or in some sequential order, then control charts are especially useful. So business managers and people that are in charge of production processes are aware that, you know, any sequential set of data can vary. The sugar content of bottled drinks, clerical errors in the bank from day to day, advertising, even the number of new customers from year to year, examples of what's called sequential data here. Now, because there's a certain area of variability in each one, we talk about whether or not a variable is said to be in what's called statistical control. A variable is said to be in statistical control if it can be described by the same probability distribution when it's observed at different points in time. And what these control charts do is it combines graphical and numerical descriptions of data within those probability distributions. Now, how do we make one? Well, first off, we recognize that a control chart is a plot of observed X values in a time sequence order. So the first thing we want to do is we want to find the average and standard deviation. You can either use past data from a period in which the process was in control, or you can use specified target values or quota values for your mean and your standard deviation. When you create this graph, you have your vertical axis, which represents x values, and your horizontal axis represents time. Usually we associate the horizontal axis with x values, but since we're measuring the values over time, we want our horizontal axis to represent time and our vertical axis to represent our variables. And so in the middle of our vertical axis, we want to draw a horizontal line where the height is the average, and you want dashed control limit lines at 2 standard deviations and 3 standard deviations from the mean on either side. The last step is to plot the variable x on the graph in time sequence order, and then we connect those dots with line segments. Now, once we finish making our chart, we can then decide or can determine if a graph or if a variable is considered to be in statistical control or out of control. So once we create the chart, the main question is, as time goes on, is the variable continuing in the same distribution, or is that distribution changing? If the distribution is continuing in more or less the same manner, we say that it's in statistical control. Otherwise, it's called out of control. Now, although sometimes it can be hard to really determine when something is in control or out of control, we can come up with methods that can set off what's called warning signals that a process might be out of control. So if it's not following the probability distribution, it may be characterized by a few things, right? So we'll assume that the target distribution is approximately normal and has target values for the mean and the standard deviation. So one of these warning signals that might hint to you that it's out of control is that one point falls beyond the 3 standard deviation level. Here's an example of that. I have 2 points here, 1, 2, where both points are outside of 3 standard deviations from the mean. Now, another out of control signal would be that a run of 9 consecutive points is on one side of the center line, which is, the target value for your average. So here I have 9 points here and 9 points here. Each of those groups of 9 points both fall on the same side of the center line consecutively. They have to be consecutive, okay? If even one of these points is on the other side of that line, then it might not be out of control. And then the third out of control signal says at least 2 of 3 consecutive points lie beyond the 2 standard deviation level on the same side of the center line, like this. So it's 2 out of 3 consecutive points. So here's 3 consecutive points. 2 of those are above this line. Here, all 3 are above this line. 3 consecutive points, 2 of those are on outside of that line, and then same thing here. So 2 of the 3 consecutive points have to be beyond the 2 standard depth mark. So here's an example. A control chart is shown below. The chart has horizontal lines drawn at the mean, at the 2 standard dev mark, and the 3 standard dev mark. So the dotted lines here are the 2 standard dev mark. These lines are the 3 standard dev mark. An engine part has been designed to have a diameter of 55 millimeters. Standard deviation process is 0.001 millimeter. So let's look for the out of control signals. I don't have any points that are beyond the 3 standard dev mark on either side, so that's good. So a lot of these points vary on either side of the center line, so I don't have a run of 9 consecutive points. Actually, I don't have any consecutive points above or below those 2 standard dev marks. So this is an example of a graph that's considered to be in control. Here's another example. A gear has been designed to have a diameter of 3 inches. Standard deviation of the process is 0.2 inches. Again, the dotted lines represent the 2 standard deviation mark. The solid lines at the top and bottom represent the 3 standard depth mark. Already, right here, I have a point outside of the 3 standard depth mark. That would be considered out of control. All it takes is one. All it takes is one outside that 3 standard dev mark. Looking at this, I don't see 2 of 3 consecutive points on the outside of the 2 standard dev mark. I don't see a run of 9 consecutive points in the same line. So, but this right here, because it's outside the 3 standard dev mark, that's your ticket to know for sure that this is considered out of control. Okay, let's practice creating a control chart here. Susan Tamara is a director of personnel at the Antlers Lodge in Denali National Park, Alaska. Every summer, Miss Tamara hires many part-time employees from all over the United States. Most are college students seeking summer employment. One of the biggest activities for the lodge staff is that of making up the rooms each day. Although the rooms are supposed to be ready by 3:30, there are always some rooms not made up by this time because of high personnel turnover. Every 15 days, Ms. Tamara has a general staff meeting at which she shows a control chart of the number of rooms not made up by 3:30 p.m. each day. Here is the a 15-day run here. From extensive experience, Ms. Tamara is aware that the distribution is approximately normal, with a mean of 19.3 rooms and a standard deviation of 4.7 rooms. This distribution is acceptable to the top administration of the lodge. For the past 15 days, here is the number of rooms not ready by 3:30 p.m. So let's create this control chart of this data, okay? First things first, we need to identify where our 2 and our 3 standard dev marks are. You don't necessarily need to put your 1 standard dev mark because it doesn't have anything to do with whether or not the process is in control or out of control. So let's go back and see what our mean is. Our mean is 19.3. Standard deviation is 4.7. Our standard dev is 4.7. So here's our mean, 19.3. I'm going to subtract 4.7 twice to get that 2 standard dev mark. Okay, 19.3 minus 4.7, so 14.6 is the first standard deviation mark, 9.9 is the second, 5.2 is the third. Actually, I can write that a little bit better. 0.2. Now going up, plus, so 24 is the first standard dev mark, 28.7 is the second standard dev mark, 33.4 is the third standard dev mark. Let's go ahead and let's graph these places here. Day 1, there are 11. That's about right. We'll put that right here. Day 2, 20. So that's right above here. We'll put that right above here. We'll connect those 2 dots. So make sure you connect them as you go. Day 3 is 25. So a little bit more upward here. Day 3 is, that's day 3. Day 4 is 16. No, day 4 is 23. So we'll go a little bit less here. Day 5 is 16. So we'll put that right at here. Day 6 is 19. So right underneath the average. Day 7 is 8. Right underneath here. Day 8 is 25. So about right here. Day 9 is 17. Here, about as close to it as I can. Day 10 is 20. So right above here. 11 is 23. 12 is 29, so right above here. Day 13 is 18. And I recognize that these might not be aligned perfectly, but that's okay. Then 14 and then 10. 14 right in the middle, and then 10 right here. Okay, so that's a rough sketch of the control charts here. That's a rough sketch here. Now, how do we know that this is in control or out of control? Let's look at the warning signs. 33.4 and 5.2 are my 3 standard dev mark. I don't see any values. I don't see any values above or below that, so that it passes the first signal. Second signal is a run of 9 consecutive points on the same side of the mean. So I don't see that. I see 3 consecutive here, 3 consecutive here, 3 consecutive here. So I don't see 9 consecutive above or below the mean. So it passes the second signal. Third signal is 2 of 3 consecutive points on either side of the 2 standard dev mark, which is 28.7 and 9.9. So I only see this point here and this point here below that line. I need 2, not 1. So this would be an example of a chart of, we would say these 15 days here, the process, we can safely say that it is indeed in control.